Hi everyone. We're going to be talking about exponential functions, and so this page will be of notes will be in your interactive notebook on page 22. So go ahead and make sure you have your interactive notebook and label it exponential functions. So exponential functions, as we discussed in class, are functions in the form of f of x equals b to the x, where b has to be a number, the base has to be a number greater than 0, and b is not equal to 1. If it were equal to 1, then it would just be a constant function, because 1 to any power is equal to 1. For example, y equals 2 to the x is an example of an exponential function. So we're going to create a table of values for 2 to the x. So just make sure that all of these notes are written on page 22 in your notebook. Okay, so when x is equal to -3, y is going to be equal to 2 to the -3, which is equal to 1 over 2 to the third, which is equal to 1/8. Okay, so 2 to the -2 would be 1/4. 2 to the -1 would be 1/2, and 2 to the 0 is, of course, 1. 2 to the first is 2, 2 squared is 4, and 2 to the third is 8. So we're going to graph these values because these values, as you can see, get smaller and smaller, but they never actually reach 0. We just need the first and second quadrant. I start with 2 to the 0, which is 1. 2 to the first is 4. 2 to the first is 2. 2 squared is 4. And 2 to the third is 2, 4, 6, 8. 2 to the -1 is a half. And then we have a fourth. And then we have an 8. Okay? And then we can go ahead and connect the points as best we can. And this is a smooth and continuous function because you can have values such as 2 to the 2.5 power, and the y value would be between 4 and 8. 4 here and 8 here, because you can have fractional exponents. Okay, next we're going to take a look at, see here, this is what I wanted, here. Okay, let's kind of make some generalizations of exponential functions. As x, well, not of all exponential functions, but this one in particular. As x approaches -infinity, the graph of y equals 2 to the x approaches the x-axis, but it never touches the x-axis since 2 to the x becomes very small, but never actually reaches 0. So it'll be 1/8, 1/16, 1/32, 1/64, and so forth. But it will never actually equal 0. So y equals 0, which is this line right here, the x-axis, this is y equals 0. That is considered a horizontal asymptote. Also, as x approaches positive infinity, the values of y equals 2 to the x increases at a faster and faster rate of change. And therefore, in the book, A Grain of Rice, the heroine, Ronnie, was able to fool the Raja because the act of doubling the number of rice actually increases to an amount that is quite unexpected after 30 days. Okay, what we're going to do next is we're going to talk about applications, growth, and decay. So now, this is actually part of your homework. Your homework on page 99 is numbers 1, 2, and I think number 3. Yeah, 1, 2, and 3. We're going to do number 1 together right now. So take out a sheet of loose leaf. This is something you can turn in, and we're going to do number 1 together. So this is not in your interactive notebook, but this is on a sheet of loose leaf. Okay. The weight of bacteria in a culture T hours after establishment is given by W sub T equals 100 times 2 to the 0.1 T grams. Find the initial weight. Well, we know the initial weight is when it is first established, and that is when T is equal to 0. So therefore, we're going to just plug in T equals 0, so the value 0 for T. So we're going to write W0 is equal to 100 times 2 to the 0.1 times 0. And of course, 0.1 times 0 is equal to 0. So 100 times 2 to the 0. Remember, first we have to take care of exponents and then multiply. And that's going to equal 100 times 1, which is equal to 100 grams. Okay? All right, letter B. Oops. Find the weight after 4, 10, and 24 hours. So we're going to continue as we did up here. So W sub 4 is equal to 100 times 2 to the 0.1 times 4. And that's equal to 100 times 2 to the 0.4. So in this case, I'm going to go ahead and use my calculator. So let's go to the calculator here, and we're going to type in 100 times 2 to the 0.4. So I'm going to type in 100 times 2 to the 0.4. And I get 131.951 grams. Okay, let's go ahead and find the weight after 10 hours and after 24. So we have 100 times 2 to the 0.1 times 10, and then 100 times 2 to the 0.1 times 24. Okay, so we can just type this in. I know this is going to end up being 1, so actually I can do that one in my head. This is 100 times 2 to the first, which is equal to 200 grams. And then this one is 100 times 2 to the 2.4, and I need a calculator for that. 100 times 2 to the 2.4. So we have 100 times 2 to the 2.4. Okay, that's an example of a rational exponent, and we have 527.803. 527.803. Okay, so 131.95, 200, and about 528. We're going to sketch the graph of WT using the results from A and B. So we know that the initial weight was 100, and then we are going to go up to 527. And our domain is from 0 through 24. Okay, so here's my graph. Just make sure that if you can use graph paper, then that would be really useful. What I did was I cut out squares of graph paper and I taped them onto my homework, and that seemed to help a lot. So if I go from 0 through 24, 1, 2, 3, 4, 6, 8, 10, 12. Okay, so each one can count by twos. 8, 10, 12, 14, 16, 18, 20, 24. Okay, and we want to go from 100 up through past 500, so 600. 1, 2, 3, 4, 500. That's actually going to be okay. So this is going to be 100, 200, 300, 400, 500, and I know this is going to be 550. Okay, so this is WT, and this is, of course, our independent variable, which is T. And we know that at 0, we had 100. At 4, we had 132-ish. 4, 132-ish. Then at 10, we had 200. It's a nice even number. But then at 24, we had 528. 24, 528, which is a little past the midpoint between 500 and 550. I want to go ahead and connect this graph because it is continuous. Whoops, I missed here. For with 538. There we go. Okay, and now what we're going to do is we're going to check our graph using technology. So again, we have y equals 100 times 2 to the 0.1x. So let's go back to our calculator, and we're going to go to graph, and then it's 100 times 2 to the 0.1 x. Okay, and I'm going to go ahead and get my window so it matches the window that I have on my graph. So window settings, let's go from, let's say, -1 to 25. And then our domain, we are going to go from, say, 0, the weight, to, let's say, 600. Okay. And let's graph it. All right. And that actually looks quite similar to what we have. If you take a look at the table, then you can see that our values are right on the spot. We have t equals 0, 100, t to the 4, 132-ish, and up all the way through 24, which was 527.803. Okay, so let's take a look at the next problem. Okay, now we're going to be talking about decay, and that is when this coefficient of the variable in the exponent is negative. So instead of increasing, what's happening to the function as x approaches infinity, the function actually decreases in value. So let's take a look at the problem. The weight, WT, grams, of radioactive substance remaining after t years is given by W sub t 100 times 2 to the negative 0.03 t grams. Let's go ahead and find the initial weight, and we know that the initial weight is when t is equal to 0. So we're going to plug that in for t, and we get 100 times 2 to the negative 0.03 times 0, and that's of course equal to, very similar to the previous problem, 100. Okay, so this is the initial weight. Now just I didn't clarify that this problem is actually on page 101, and these are the decay problems. So you want to leave space after the previous problem because there's two other problems you need to do, and then these are the set of decay problems. Okay, let's go ahead and take a look at the next problem, which is to find the weight after 10 years, 100 years, and 1,000 years. So we're going to do 10, which is W sub 10 is equal to 100 times 2 to the negative 0.03 times 10. Let's write that again. Negative 0.03 times 10, which is equal to 100 times 2 to the negative 0.3. Okay? And let's go ahead and just figure out what we're going to put in our graphing calculator, and then we'll do them all at the same time. So W sub 100 is equal to 100 times 2 to the negative 0.03 times 100. And that would be 100 times 2 to the negative 3. And then after 1,000 years, we would have 100 times 2 to the negative 0.03 times 1,000. And that would be 100 times 2 to the negative 30. The decimal point moves 3 positions. Okay, so let's go ahead and figure these out. 2 to the negative 0.3, 2 to the negative 3, and 2 to the negative 30. So we're going to go back to, actually, we're just going to add a new page here and use our calculator. Okay, so we're going to have 100 times, is it 2? Yeah, 2 to the exponent, and the first one was negative 0.3. Okay, and the next one is 100 times 2 to the negative 3. And the next one is 100 times 2 to the negative 30. Ooh, I want that as a decimal. So, there, ooh, wow, that got really big. That's scientific notation, 9.3 times 10 to the negative 8. I'm sorry, really small. So that got small in a hurry. So the first value is 81.2. We'll round to the nearest tenths. The second value was 12.5, 25 halves. And after 1,000 years, that would be 9.3 times 10 to the negative 8. Let's actually do 3 significant figures. So 9.31 times 10 to the negative 8. If we're going to graph it, gosh, this scale is pretty hard to do here. Let's see. Okay. So if we want to graph this, the x values go up by quite a bit and not at the same rate. And the y values are going down, but that's easier to graph. So the x values, we want to go up to 1,000. So we're going to have 1, 2, 2, 4, 6, 8, 10. So let's say this is 1,000. So that would be 100 here. Okay, and then 10 would be right about there. So this is W sub t. This is t. So the initial value was 100. So 20, 40, 60, 80, 100. After 10 years, it was 81. So this was 80. So about here. After 100 years, it was 12.5. So it goes down pretty quickly here. This is 20. So 12.5 is about here. And then it kind of tapers off. And this is 9.3, which is very, very close to 0. Okay, so now if we graph this, we have a function which is tapering off and gets closer and closer to 0. Okay. Now, we're going to find the time when 10 grams of substance remains. So 10 grams of substance is going to be after 100, and we want to use technology to do this. So let's go ahead and go back to our calculator, and we're going to go to graph. And let's plug in the equation. So we have 100 times 2 to the negative 0.03 times x. Okay. Now, the window is not quite right, but what I really want to do is I want to look at the table. So let's go to the table. When there are 10 grams of substance remaining, so let's just make sure our values are correct here. So 10 to the 0 is 100. 10 to the 10 was 81.2. To the 20th, or no, we didn't do to the 20th, we did to the 100th, which was 12.5. And 1,000, we can scroll all the way down, but we want to know when it's 10 grams are remaining, and that's going to be about 110 years. Yeah, between 110 and 111. So we can say about 110 years. Okay, so find the time when 10 grams of substance remains. Approximately 110 years. Okay, so we need to go backwards. We're given the WT value, and we want to know the T value, okay, the inverse. All right, express the amount for the amount of substance that has actually decayed. Now, we know that this is a function that shows us the amount that remains. So what is the relationship between what remains and what has actually decayed? Well, after, say, the 10 years, we had 81.2 remained. How many decayed? How much actually decayed and was no longer part of the weight? Well, that means that originally there was, I'll do this in a different color, 100. And this is what remains. So what decayed? Whatever was taken away, right? And that's what was actually decayed. So that means to get to the decay, we take 100 minus W sub 10, okay? So it's going to be 100 minus W sub T, which is right here. 100 minus W sub T, because 100 is the initial amount, or initial weight of a substance. Okay, I hope that was helpful, and let me know if you have any questions. Thanks.